Hello everybody, my name is Masuzio, and I'm here to talk to you about moments and how to solve for moments about a specific axis. So here we have our example problem that's in the PowerPoint, and the given information is here. We have 200 pounds going 3 feet from this point over here, and then here's another 3 feet. We have more force going 3 feet, another 3 feet over here, and then 3 feet. So total, this is 9 feet long, and we have a force acting 9 feet away, another force acting on A, and it's 6 feet away, and then there's one that's just 3 feet away. And I'll label everything correctly, sorry. And so what we're trying to solve for is a resultant force a specific distance away from point A. If I wish I could ask for questions, right? But so find the equivalent resultant force and couple moment acting at A, and then the equivalent single force location measured from the point A, right? Well, how do we even start this problem? The first thing we're going to do is we're going to find the sum of all fx, and notice that A, our point A, lies on the same axis as our x-axis, right? Therefore, any forces that go in the x direction will not show up in our moment equations. And I'll give you an example just really quick. I'll draw it out for you. So let's look at 200. This one's easy, right? You just have to, so here's a straight line. And then another one. So 200 going straight this way. And then this one will have 100 LB, but remember I'm going to draw the components, right? And then notice that this lies right on our line of action. So any forces that go in the x direction are canceled out because of internal forces in the bar cancel out the forces in the x. And the fact that it's also fixed to a specific point means that there's going to be no motion in the x direction. There's also going to be no motion in the y direction because that's part of the question, right? We have to understand all this in order to solve this problem. So we look at, here's our x component, so we'll call this, so that's A, so we'll call this point B, we'll call this C, and then we'll call this D, right? And then this would be 30 degrees, and boom, 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 boom. So those are the components. And then there's our, so then we'll call this CX, this would be CY, this would be this would be dy, this would be dx, this would be cy, and then this force here will be cx, and then this one we'll just call it by. So we'll call this by. Right? So now that we have that set up, we can start finding our equations for all the forces that are going in the x direction. So we know that it's all going to equal 0, as I said earlier, because there's no motion. Statics only deals with things that are not in motion. So just because there are forces there doesn't mean there's any motion. So we're going to say it's equal to 0. And then we're going to, any forces that are going in the x direction, we're going to put them here, right? And we have our dx and a cx. So those are the sums. So we got cx. Oh, plus I forgot about a. So as I said, there's internal forces, and the internal forces act at A. So there could be some AY, we don't know, we might not have one, and we could also have an AX, and we don't know what that is either, right? So now we have everything we need, and we're going to start. We're going to say CX plus DX plus AX, that's the sum of all our f of x. Now we're going to do sum of f of y is 0. What do we get? We'll have AY plus BY plus CY plus DY. And so CY has to be minus because it's going downwards, right? And there's another equation that we have. And now we're going to go for we're going to sum all the moment about this axis. Sum of all m is going to be equal to 0, right? So we're going to have a moment that's about A. Why do we have a moment about A? So if you read through the textbooks, they'll talk about the type of points that are fixed and not fixed. And because this is a fixed point, meaning it's screwed into the wall, right? There should be a moment to cancel out the moment caused by all these forces over here. Otherwise, it will just start to rotate. If it was a pin like this, so this is just a pin, and then we had the bar just hanging out over here, then we know there can't be a moment about A. There just will only be an AY component and an AX component. We can go over that more if you'd like. But these are like little things you kind of have to know in order to solve this problem. Okay, so now we're going to go and do the moments. So the way I'm finding a moment works is you take the distance, which would be 3 feet here, and it would be 3, so yeah. And remember, we don't have to worry about the x components because they won't show up in our moment equation because they're all pulling right on the axis, the line of action, and because they're right on the line of action, they only produce forces internally, not externally, right? So this is something I wish I was more aware of whenever I took statics, which is that there's a difference between internal forces and then external forces. So here's a particle, right? Here's like a ball, right? What's keeping that ball together are internal forces. Internal forces that cancel each other out. And you can have many, many internal forces like that. But the overall motion of the ball, like you hit it with a baseball bat, right? It causes a force. So the internal forces inside keep the ball together from breaking into small pieces, and then also they help translate that motion or that force of contact, that impulse into the ball, which creates what we call a force, an overall non-internal force that pushes the ball away from the bat, right? But you can still have internal forces. And what I'm trying to point out here is that the CX and the DX lie on the line of action and will not cause the bar to move up or down. So we don't have to worry about that in our moment equation because we only look at the forces that cause torsion or movement up or down, right? So we're only going to take these forces. So we're going to take BY. So it would be BY times the distance from point A, because part of the question asks us to find the couple moment at A. So we're going to take the moment at A. So the sum of all moment with reference to A is what I'm trying to say, with reference to A. So we have the sum of all M, which includes the moment that is at point A, but we haven't gotten to that point yet. And we're going to do BY, so we get BY times 3 feet, because that's how far it is away from the A point, so this is point A. And it's going up, and we have to determine which ways are positive. So we're going to say rotating this way is positive. So clearly this is rotating that way, so that's why it's positive, right? And then what about C? Well, we're going to get plus CY, right? Or minus CY because it's pushing it this way. So we get minus CY times 6 feet. And the reason why it's 6 feet because we have 3 feet plus 3 feet right? And now we're going to go minus, oh no, it'll be plus this one, sorry. This one would be plus because it's going up and around this way. So clockwise would be this way. So it's going counterclockwise, which means it's positive. And we have dy here. And remember, it's 3 feet away, so right, 3 feet here. So that's 3 plus 3 plus 3. So we'll get 9 feet here. And then, of course, we have to subtract the moment that is at A, because we know it's going to be equal to 0. So we'll get at this minus A, the moment at A. So the moment at A. Yes. And this is something we need to solve for, right? That's what we want to solve for. So we're going to get MA is equal to BY times 3 feet, and then minus CY times 3 feet plus 3 feet, and then plus DY, and it'll be 3 feet plus 3 feet plus 3 feet, which equals 9, right? I'm just showing you the process that I went through. And now we need to solve for BY. We have these parts done, and that's solved for already. So how do we solve for BY? Well, BY is at 90 degrees, so we're going to say BY is equal to sine 90, which is just 1 times BY, the magnitude of BY, right? So that means we'll get BY is equal to just 100 lb. All right, let's solve for C now. C, we have a 4, 3, 5 triangle, right? So we could find the angle over here, or we could just simplify it to what we know about 3, 4, 5 triangles, which is that it would be the magnitude of CY times 4 over 5. The magnitude of CY, sorry, so we're just going to get magnitude of BY here times 3 feet. And we know BY is that. And we know that means that CY, I'll write it over here, CY is going to be equal to, I meant 200 for BY because it says 200. I just looked at that wrong, my bad. It's 200. Cool. And then CY is going to be 100 times 4 over 5, right? So I won't have to put that in there. I'll just leave it like this. And then, yeah, so I get just CY. Sorry, if I were to write it fully out, we'd have CY is equal to the magnitude of C times 4 over 5, which is going to be equal to 100 times 4 over 5, which is equal to 80 laps. So we're going to plug it in later, in just a little bit. So that's CY. Now we have to solve for DY. So DY would be like this. We have DY is equal to, well, we have 30 degrees, right? And it's reference to the y-axis, right? So if we want to find the force of dy, because this is 50 pounds going in this direction, we're going to have the magnitude of d. I hope you understand the double bars mean its magnitude. That's my notation. It just makes it easier for me to understand what is the magnitude, what is not magnitude. And then of course we're going to do cosine 30 degrees. And the reason why we do cosine is because we have the angle reference to the y-axis. We could also have done sine of 60 degrees in order to solve for dy. And that will give us, so it would be root 3 over 2 times 50. So then we can just turn this to 25 root 3 LV. Cool. right? So now let's plug in our values here. So we get 200 lb times 3 feet minus, and that'll be cy, so then we'll get 80 lb times 6 feet, and then we'll have plus, and remember this is equal to ma, right? Plus dy, which will be 25 root 3 lb times 9 feet. And here we are. We can solve for the moment about a now. And we sum all these numbers up together. So we'll get 600 minus, all right, so 6 times 8 is 48, so it'll be 480. And then this would be 25 times 9. 25 square root 3 times 9, and we get plus 380, 9.71. And I'm going to just double check my solution that I solved before and see if the numbers I get are correct. Okay, so we're going to do 600 minus 480 plus the answer. And we get indeed what the book report should be, 509.7 lb per foot. And that's equal to m at point A, the moment at point A. Cool. So now we're going to we have to sum all the Fy, so all the forces in the y direction, and well, we've solved for these, right? So we're gonna add them all together. And we're going to solve for AY, because we need to know what AY is. So this is what we're going to do. And we'll get AY is equal to BY, so it'll be 200 LB. And then we'll get minus 80 lb plus 25 root 3 lb. That will give us, so 200 minus 80 plus 25 times root 3. And we will get 163.3. And that will be in pounds, right? So now, we have two things. We got, I'm going to circle them, so we got 163.3 lb is equal to AY, and then there it is, right? So we want to figure out we've just solved for the resultant moment caused by all these forces going about the axis, the a-axis here, and we figured out that ma, which is the force or the moment required to stop any motion happening in this bar, is going to be equal and opposite to that force right there. So there's a force of 509.7, not force, there's a moment of 509.7 foot-pounds, right? Going in this direction, right? In the positive moment direction. And therefore, the moment about A has to cancel that out, otherwise there will be movement, and it will be rotating, right? And we don't want any of that. So, yeah. So that's why the MA is equal but opposite to this number here. And then we know that the resultant force, after we solved up all the AYs, the equivalent resultant force that's going in the Y direction is equal to 163.3 pounds. And now we want to figure out how far this force is from our axis point. And this is where we do, it's very easy to solve for. So the units of AY are in pounds, right? And the units of the moment are in foot-pounds, right? So what we are going to do is we're going to do 509.7 lb times foot divided by 163.3 lb, and the feet cancel, and we can solve for the distance from the x. We can solve for the distance from our initial starting point, or yeah, so where the resultant force would be equivalent to all this, and we should get